Hardware RAID is dead. Okay, you might not have gotten the memo about that, so you should for sure check out my other video if you didn't see that. Today's more about, okay, if it isn't dead, it's certainly got to be on life support, right? And saying its final goodbyes. But more answering the question, what fills the void that's left behind? I'm not dead yet. I don't want to go on the cart. I'm getting better. I think I'll go for a walk. I was surprised how many of you wanted to convince me that hardware RAID wasn't dead, even when dealing with our Kioxia CM7. You realize that these NVMe SSDs can do like 12, 14 gigabytes per second individually? They're PCIe Gen 5. Let me walk you through my reasoning step by step, because clearly, I can tell you it's not planning for the fjords. Not only is it dead, for the common arguments for why it shouldn't be dead, a single CM7 will take a lot of the wind out of your reasoning. But what about the latency? And it's all about the IOPS. 2.7 million IOPS for a single drive, and this is NAND flash. It's nothing special. Okay, it is special because Kioxia, but you know what I mean. I think a lot of you are more worried about how to fill the void if it is dead than what to do if it is dead. So let me take the worry about that out of the equation. There's actually several ways of filling that void that can be approached today with what's available today, and we'll talk about that too. Sometimes a piece of software or an application is already designed to deal with an array of block devices directly. You don't really need a RAID volume that's less overhead than a RAID card would be anyway. So it's kind of a combination of hardware and software maybe that could make more sense for some of these. I mean, Microsoft's working on their ReFS file system, which, like ZFS, wants to work directly with block devices and not via a RAID controller. But before we get to that, let's talk about why it's tough to get block device performance matching even one or two of our Kioxia CM7 from a hardware RAID card. The answer really is hardware RAID technology is evolving. In a short time frame, we've gone from a server CPU having 16 or 28 or 32 PCIe lanes to 128 PCIe lanes. That's pretty much across the board, whether you're Team Red or Team Blue. 128 PCIe Gen 5 lanes. Now we've got 8 of these Kioxia CM7 PCIe Gen 5 using a U.2 form factor, but they are available in E.1 or E1.S and E3.S and U.3, other form factors as you need them. And like I said, this Gen 5 SSD is capable of up to 14 gigabytes per second, 2.7 million IOPS. That's nearly saturating the bandwidth of 4 Gen 5 lanes. I mean, look at our Crystal Disk Mark performance here. This is just baseline to give you an idea. For the hardware RAID is dead video, a few of you conceded that yes, a hardware RAID controller will be a bottleneck for this top line throughput number. But you say it's not about the throughput, it's about the IOPS. Well, even one of these drives is gonna, okay, we'll take a look at that. There might be something to that. Not really, but we'll take a look. Just remember that one of these Kioxia drives moves as much information as a Gen 3 video card. Yeah, 16 Gen 3 lanes, same as 4 Gen 5 lanes. That's not to say that the random I/O, low queue depth performance is not important. Actually, that is probably one of the most important things. I mean, you are right. And a RAID card with a large cache will improve those low queue depth I/O operations without letting some of these high-speed devices get bogged down with a lot of small requests. And if you think about it, like, you know, you have a server hosting a bunch of virtual machines, whether they're hosting virtual machines for workstations or a database server or whatever, generally you're not running at 12 gigabytes per second, you know, flat plank all the time. You just need a few hundred megabytes here and there from random I/O, from tasks running in the background. So the reasoning is sound that a RAID card bottlenecking the top line performance, and it's really more about the I/O operations per second, is sound, but it'll all fall apart under scrutiny. Really, when we're talking about IOPS, we're talking about latency. And there is a relationship between the latency floor, the fastest time that you can get a request in and out, and the overall throughput for that. I mean, latency effectively is lowered by the RAM on a RAID card when you can serve the data from the RAM cache on the card. The RAM on the card is going to be faster even than our CM7. That makes sense. But most of the time, you're going to be a cache miss, and that causes latency stacking. You get the latency of the cache miss plus the latency of the RAID card asking our CM7 for the block anyway. So generally, it'll be worse. I mean, it's worse except when you get a cache hit, but most of the time, you're not going to get a cache hit. And in fact, NVMe is so fast that a lot of modern RAID controllers don't even cache reads. They just cache writes, and it does help with writes, but one thing at a time. So it turns out that these NVMe devices are so fast, they're driving changes in how the operating system handles block and I/O devices. Yeah, turns out. Back in the day, when you would have a block device like this, it would use interrupts to notify the CPU. The CPU would say, here's a block of data, you need to do something. And then the block device would do something with that and then send a software interrupt to the CPU to say, hey, I'm done with that, give me the next thing. But these modern drives are so fast and they complete those kinds of operations so quickly that it's actually usually more efficient and faster to poll the drive rather than using interrupts. If you've been a system administrator for a long time, that sounds heretical. But this is the reality that we find ourselves in. CPU cores are so fast, and the bus is so fast, and the drives are so fast, that the overhead of servicing that interrupt is considerably higher than just polling the drive. And that's what the Linux kernel does by default now on most NVMe devices. These Gen 5 devices are so fast that putting the RAID card in the way, it hurts latency even before we get to thinking about the benchmarks. That's another way I could explain this. Whenever we are trying to characterize the performance of storage, we're concerned primarily with two things. The throughput, that top line number in crystal disk mark, how fast is the darn thing, and latency. And we talk about latency a couple of different ways. Sometimes we say it's low queue depth, sometimes we say it's queue depth 1 performance, but really these are different ways of describing latency. How fast does it take to get a single block? I'm going to ask the device for a single block of data. How fast can I get that single block of data back? Because real world random I/O, a lot of the things that are happening on servers or workstations, less so on servers, more so on workstations, has to do with these low queue depth operations. You need to get a block from disk before you know which blocks you need next. So, by way of explainer, think of me. I'm your block device. I'm going to fetch blocks for you. This is probably the easiest way I can help you build a mental model of this if it's not clear. So it turns out that in our mental model, if you think of me, I can complete a request to read a block in superluminal time. It takes me 0 time. You think of a block and I give you the block instantaneously. I get to rest for a second after I give you the block, but to make this exercise simpler, it's just instantaneous. So you ask me for a block of data. Instantaneously, I give you a block of data. But before you ask me for the next block of data, I get to rest for 1 second. I'll also say that I can carry up to 100 blocks at a time. So if you know in advance which 100 blocks you're going to need, I can bring you all 100 blocks instantaneously and rest. But if you don't know which 100 blocks you need ahead of time, then you're going to have to wait 1 second in between each request. So you come with your first block and it's like, well, I don't really know which blocks I'm going to need, but the blocks that I'm going to need are contained in the data of block 1. So go ahead and get me block 1. So I bring you block 1 instantaneously. There's block 1. You look in it and you say, oh, now I need block 2. Well, I have to wait 1 second before I read block 2. I give you block 2, and then inside block 2, it says, you're going to need block 3. It's like, okay. So I go and I get block 3, and I give it to you instantaneously, and then it's like immediately you say, oh, I need block 4. So how long is it going to take me to give you 100 blocks? It's going to take 100 seconds. But if you knew ahead of time exactly which blocks you needed, you could give me the full list of 100, and I could deliver them instantaneously. This is the relationship between latency and throughput. If you can keep me fully loaded, like I can carry 100 things at a time, if you can tell me which 100 things you need, then I can bring those to you instantaneously 100 at a time. But if you can't keep me fully loaded, if you don't know ahead of time which blocks you're going to need, I can only bring you one at a time. That round trip latency, making you wait 1 second between requests, that's going to kill our throughput. It's 1/100th as much, potentially. Now suppose we're in queue depth 1 request mode, and the first block you asked me for is 1, and the next one really was 2, and the next one is 3. I can look at this list of blocks, after we're 3 or 4 seconds into this and say, I'm not doing anything anyway. I'm just going to go ahead and bring blocks, number 2 through 100. And all of a sudden you come back to me and you say, hey, can you bring me block 3? I wasn't clairvoyant. I didn't know that you needed block 3. I just looked down and said, okay, you asked for 1 and 2. I'm not doing anything anyway. I'm going to go ahead and bring blocks 3 through 100 because I can carry up to 100 at a time. And yeah, that worked out for us. That was instantaneously, dramatically way faster. This is more common of a thing that's happening underneath in individual NVMe devices than people realize. In the olden days, that was something your RAID controller would do for you. And it still is, to an extent. A RAID controller can figure out the access pattern. It can go ahead and algorithmically guess and prefetch whatever blocks it thinks are going to be needed. But it's not a given necessarily. There's a lot more of that kind of thing happening under the hood with modern storage devices than most people realize. And sometimes it's even happening at an operating system layer. The operating system's looking at it and saying, let's just go ahead and queue up all these requests. So the other thing to look at in benchmarks is how many queues do you need to fill to get to our 2.7 million requests? Certainly less than 32 parallel requests at once. And sometimes there's a mathematical relationship between our queue depth 1 latency and the maximum number of I/O operations per second. Sometimes our max IOPS is lower than expected, and that's usually a situation where the processor on the storage medium, like the processor inside the NVMe, is slower than can keep up with our queue depth 1 performance, because real world, it's not actually queue depth 1. I mean, even in a completely fair coin toss, you're going to get, 6 heads in a row tossing between heads and tails. That's a thing that happens even in purely random situations. And real world, with server workloads with thousands of clients, it's not truly random. Usually it looks random, but it's really not. And there's little things you can do to predict the load. So anyway, let's look at performance of our hypothetical NVMe RAID controller to see that, we're just doing napkin math here, and the napkin math is not going to work out for us. We got 4 of them, just 4. I want to run 40 gigabytes per second of throughput. That's taking out some serious overhead. And I want my low queue depth performance overall to basically be the same, because it shouldn't get any worse, right? So 16 lanes of Gen 4 PCIe just isn't enough to keep up with 4 drives times 4 lanes of Gen 5 storage. Some of you already conceded that on my Hardware RAID is Dead video. It's like, okay, but what about IOPS? Because the low latency and the performance and the caching, those things can make up the difference, right? That'll create the overall better real world performance in the way that, a very low latency storage block device like Intel Optane will have a better queue depth 1 experience. And so it'll feel faster than even the highest end NAND flash-based device. Because the latency floor of an Optane type device, which is a different physical memory medium than NAND flash, it's like half what NAND flash is. So those low queue depth performance numbers are always going to be really good, even though that top line number for raw throughput is not as good on Optane as it is on modern NAND flash devices. And so you might think caching is a solution. Well, your CM7 can do 10 gigabytes per second in its sleep per drive. 32 gigabytes of cache wouldn't be an unreasonable start on a hardware RAID controller, but a lot of these highest end RAID controllers you can get, like from Broadcom, well, there are only 8 gigabytes of RAM, and that's it. And most of the time, algorithmically, that RAM is not used for read caching because the reads are so fast anyway. It's to speed up writes. The Mega RAID 9670 is one of the highest end controllers you can get, and it does have its place. I'll admit, there are places where it can work, but you've only got 24 Gen 4 lanes to work with, and it's 16 Gen 4 lanes to the host. When I talk about this 8 gigabytes as a write buffer, that's going to give us, a second or two of low latency battery protected memory, which can improve random write performance. That is true. A lot of the time, the cache machinery makes the latency worse, so these controllers don't bother with read caching, because putting something into the cache memory and then cache missing most of the time, unless the cache is absurdly huge, is more latency than just asking the CM7 to begin with. So more often than not, these RAID controllers simply will not cache reads because the drives are already fast enough in terms of reads, and the cache size on the card is just not large enough. Wait, what? Yeah, it's clear from some of the comments that a fair number of you don't understand that. And when we're talking about enterprise solutions, like truly enterprise solutions where you've got racks and racks and racks of stuff, they are a lot of the time using system memory as a read cache, not the cache on the RAID controller. The cache on the RAID controller typically is just used for transaction logging and write caching. I mean, the memory on a RAID controller is about 20% or 1/5 the latency of NVMe. It can be really good, but it's not the wisest use of the cache on the card because it's not that much faster. And the problem with the latency stacking means that just having that there in the pipeline is not a great idea. You generally, for reads, want to query the device directly. So that's why the design of these kinds of things has gone in that direction. Now, theoretically, could you add more than one of these RAID cards to a system and have them work together? You know, you got 24 lanes, and say you add 4 of those to a system that'll use 64 lanes, let you fully populate a 24 drive NVMe 2U RAID chassis. Theoretically, you can do PCIe to PCIe transfers without involving the CPU, but there's no RAID card I know of that does that. I think I'll go for a walk. You're not fooling anyone. A hardware RAID device like this might make sense if you got a backward operating system or a weird edge case that you're looking to make ends meet on. You know, a RAID 1 or RAID 10 volume with like 2 or 4 drives. Okay, maybe. But I'm talking about these chassis where we've got 8, 12, 16, 24 4-lane NVMe at the front of the chassis, and you want maximum performance, minimum latency. The NVMe performance here is just far outpacing any theoretical RAID controller that can handle it. I mean, it's not just practical because PCIe slots are only 16 lanes wide, but because you won't win in a latency versus direct attached storage type scenario. Fortunately, the void that this is creating is already filled for a lot of common use cases. One of the most common use cases for the solution that itself is kind of adapting in there is databases. Databases that is high volume and low latency. A lot of database software has gotten new engineering the last couple of years to actually spread the database data out over physical volumes. It's basically RAID at an application level. I mean, yeah, it's neat because you can mix concepts like RAID 10 for hot data and RAID 5 for economy of space. And though most database systems are moving away from having any kind of like system level storage redundancy, instead opting for a clustered solution to get redundancy back, meaning you have multiple database servers, and if one little thing is wrong with the database server, the whole database server falls out of the cluster. But you also have other companies like Microsoft pushing ReFS and solving the problem, again, kind of at an application/operating system level. There's also ZFS and BTRFS. ZFS isn't there in terms of efficiency, but it's definitely there in terms of redundancy and failover and not needing anything special in the way of a RAID controller. But on Linux, there's MD-admin, or multi-device, or Linux's software RAID, and that actually is a really competent solution, it turns out. The biggest problems with software RAID is that it's hard to guarantee writes are synchronized across the physical devices. We like to abstract away, it's like I've got a bunch of physical devices, I just want one logical big block pool of storage. Hardware RAID cards have a battery backup unit or a large capacitor to store a little bit of stuff in memory to ensure that when the system comes back on after a crash or power loss, that the drives are all consistent with each other. You can't be guaranteed that they all lost power at precisely the same moment. LinuxMD cleverly approaches this problem without the need for a battery backup unit to ensure that the system is consistent. It really works best when the RAID system has some insight into the file system that's running on it. LinuxMD has some clever approaches to dealing with this, but the main disconnect for closing the write hole is that without a guaranteed consistent log of what's been written, the RAID system kind of needs to know what's going on at the file system level in order to ensure that the file system itself is consistent after a crash. Now, Intel, for their part in this, they've contributed much of the engineering development on LinuxMD, including some of the approaches that they've patented to closing the RAID 5 write hole without using a battery backup. And they're part of, those approaches are part of Intel's virtual RAID on chip, or VROC, enhancements to LinuxMD. For file systems like ZFS and ReFS, and even to an extent ButterFS, BTRFS, the RAID 5 write hole isn't really a problem because those file systems themselves have been engineered with multiple physical block devices in mind. The file system takes care of pooling a whole bunch of devices and solving the RAID 5 write hole themselves. So the only thing that you might bring up if you're still on team not dead yet is CPU overhead. Doesn't it take a lot more CPU overhead to do the RAID in the CPU as opposed to an add-in card? Well, yes, but also no. To be clear, we're talking about CPU overhead for parity calculations only. The CPU overhead for moving ginormous blocks of data around is almost non-existent in modern OSs. But for parity calculations, there are some interesting approaches that are out there to fill the void, including companies like G-RAID using a GPU to do RAID parity calculations. This might be cool, but it still relies heavily on both the CPU and the GPU to do the work. There's a hardware part of this RAID solution, but it's not a hardware RAID solution, if that makes sense. Linux MD also lets you reserve cores for parity calculations or limit the number of cores doing parity calculations, which is really super handy and is basically not a performance bottleneck on modern systems because of things like AVX 512 and AMX acceleration for this kind of thing. But in a modern multi-core system, if that really is a concern, you can choose a lower overhead RAID geometries or just buy a CPU with more cores. By way of a tangent, Linux MD and all software solutions that I'm aware of depend on the underlying devices to actually report read errors or read inconsistencies. This is, of course, not true with ZFS and BTRFS and ReFS, but you can put that functionality back with Linux MD with DM integrity. And the NVMe specification also has a data integrity field, which I talked a little bit about the old version of that on Mechanical Spinning Rust in my Hardware Rate is Dead video, but the data integrity field is kind of making a comeback to give us more knobs and tunables and more facilities for detecting errors on read that are not detected by the underlying devices in a relatively low overhead kind of a way, which is encouraging to see. If verifying information on read is important to you, you should be aware of those caveats because, well, there's not a lot out there that does verify on read except for ZFS and ReFS and BTRFS and things that are designed for these problems in mind. So again, there's different ways to fill the void. It's not just one thing that drops in for the hardware RAID replacement. You've got options. Speaking of things that plug in, a third thing that's nice to have is PCIe hot plug, and support for this varies from platform to platform. Theoretically, if your NVMe plugs into a controller, then the host doesn't have to support PCIe hot plug because you're plugging and unplugging a device from a controller. That's really nice. It solved a lot of problems in the olden days with normal RAID controllers. 48 PCIe lanes to 24 drives, let alone 96. I was quite surprised to learn how this works with Intel Vroc under the hood. If you haven't heard of Intel Vroc, Vroc is Intel's virtual RAID on chip solution. It is software RAID mostly, but I think it's actually probably more accurate to call it hybrid RAID because there are hardware features to it. It's mostly software. It's available on Intel Xeon platforms, and it is a separately licensed feature, meaning that you need a key to unlock it, whether it's on Workstation Xeon or Server Xeon. When you do enable VROC, it reconfigures the PCIe root bridges in the processor to change how the NVMe slots connect. It changes the bus numbering and some other root port parameters to better support hot plug and to better support a huge number of removable NVMe devices. That's pretty awesome if you use port multipliers or anything like that. So Intel's done some engineering here. VROC also enables out-of-band management. You can manage your Linux MD array from the remote IPMI system on your motherboard and add and remove drives, take them offline, get logs. Yeah, VROC will let you do that. There's actually a separate mailbox device that gets set up when you set up the Linux MD array the VROC way, and that enables a communication layer between the actual VROC driver and the out-of-band management, which is really actually pretty awesome. If you dig into it, a lot of the Linux MD programmers are actually Intel programmers, and so Intel's responsible for a lot of the development on Linux MD, it seems like, even though these features do require a license unlock. Of course, now most of it is present in Linux MD. You don't need a license unlock to use it. It's software RAID. You're going to get the software RAID performance benefit. But if you do have VROC, you can get a small performance bump, and the VROC volume works the same on Windows as it does on Linux. That means you can dual boot and mount the same volume. And there is no faster option with these Kioxia CM7 with native Gen 5 support at Gen 5 throughput and latency on Windows than Intel's VROC solution. Setting up these arrays with 8 of these CM7s really couldn't be easier with this setup. And even under Windows, it is breathtakingly fast. So this is Crystal Diskmark, but I really ramped up the number of queues and threads because, well, this array can do 40 gigabytes per second with just 4 CM7 drives. This is VROC on Windows. Wait a minute, is he saying that VROC is our mythological future for RAID with high-speed NVMe devices? Yeah, Intel engineers figured it out a long time ago. Regardless of how Intel is marketing it, VROC is the right combination of hardware and software to really dot the I's and cross the T's for how these arrays should be. Closing the RAID 5 write hole, not necessarily even with battery-backed RAM or static RAM. I mean, they did build themselves a way to do it with Optane, but that's another conversation. You don't need that. It works really well. You get out-of-band management, you get all the enterprise features that you need, and Intel has also left themselves a way to be able to do really inexpensive context switches for data transfers. So even if you're moving things in and out of your AVX registers or your AMX registers, the overhead for switching context from a user process to a kernel process for those IOs is potentially very low overhead. Right now, it's Linux MD, but on other operating systems like Windows, it's a first-class experience. It's even a better experience than ReFS right now for everything except data integrity. So, yeah, Vroc kind of is what it's going to have to be to solve a lot of these engineering problems. Shocking, I know, but Intel engineers sort of know what they're doing. I went down a rabbit hole here looking at Vroc performance on Linux MD native and then just Linux MD performance and then also LVM performance because LVM under Linux, the logical volume manager, also uses some of the Linux MD code under the hood. And Linux MD is lower overhead than LVM and faster, especially on the Vroc side. At the end of the day, digging into Linux MD for the options that it gives you for closing the RAID 5 write hole and some of the other options that it has under the hood, it basically addresses a lot of the concerns that I have about hardware NVMe RAID. Not only that, but if you use something like DM integrity to also get read verification on, reading back from your array, that sort of closes all of the concerns that I have about hardware RAID for really high-speed devices in 2023. And you, the end user, if you're a system administrator and you say, I'm going to trust the devices to do the read verification, I don't need that level of performance. That's cool. Sign off on this form here that says that you're aware of that and run that with your solution and good to go. Because if there's ever any kind of data corruption or bit rot in the future, well, there'll be a paper trail and there'll be fun stuff to do for that. Otherwise, you can run, DM integrity or use the data integrity field on your NVMe device or move in that general direction or just verify your backups or whatever. It's all good. And just to make sure we're clear, I'm not talking about Vroc on the desktop. You can do Vroc with SATA devices, which has never made sense to me. That is not a good user experience, especially when we're talking about boot volumes. I mean, maybe it would make sense for a data volume, but, there's just not enough PCIe lanes and not enough connectivity on desktop LGA 1700 processors for this kind of thing to apply that I'm talking about. You want to run 2 Gen 5 SSDs on a desktop platform. There's not even Gen 5 connectivity for storage. It's only the one X16 slot. And getting a motherboard that breaks that out, we're not talking about that. And Vroc did apply to SATA devices way back in the day. It still can. Maybe that makes sense for bulk storage devices, but I'm really not talking about that. I'm really talking about for the future PCIe storage, that kind of connectivity. That really only applies to platforms where you've got at least 40 PCIe Gen 5 lanes like Xeon Workstation or other workstation platforms. If you've been following this project on the Level 1 forums, you'll see that I've had a lot of fun sort of poking at this. So again, because I had a lot of questions, Intel invited me to Innovation 2023, where I got to meet a lot of folks that work on this and get a lot of my questions answered. So big thanks to Intel for making this video possible, and big thanks to Kioxia for sending me the hardware and also answering questions and giving me the stuff to experiment with. And Intel Vroc, it turns out, taking all the PCIe lanes into the CPU for all the storage you could ever need is already more or less what we need to fill the NVMe RAID void, assuming that your software doesn't have a better option built in. It's the best of both worlds in terms of latency and throughput, and it's available for free basically on Linux, unless you want out-of-band management, then you do got to get the key. Or if you're on Windows, then you also got to get the key. But you got 100 PCIe lanes of Gen 5, and you want those Gen 5 lanes to go burr, then this is probably the best option for you. I'm Wendell, this is Level 1. This is a look at, okay, if not hardware RAID, what then? What? I'm signing out. You can find me in the Level 1 forums.